Alrighty, hello again Method students. In this video we're going to continue on with 16C and looking at these worded questions to do with normal distributions. In these next two examples we're going to see some, I suppose, more complicated questions that apply a couple of tricks that will be handy to have in your toolkit moving forward. So for example 2 here, we've just got this note that says, when the mean and standard deviation of a normal distribution are unknown, it is sometimes necessary to transform to the standard normal or to use the standardized values, which we call z-scores sometimes. It says here when the mean and standard deviation are unknown. In actual fact, when either one of them is unknown, this rule can be useful. Let's have a look at how this works in an example, and hopefully you'll kind of make sense of it as we go. So in this question, we've got a machine that's being used to cut metal screws, and it's found that 8% of the metal cuts are shorter than 12 millimeters, and 5% of the metal cuts are longer than 19 millimeters. And it says, assuming that the distribution of metal lengths is normally distributed, so there's that phrase that we look for these questions. Remember, we don't just assume that something has a normal distribution, the question should tell us. We have to find the mean and standard deviation for the length of metal cut. All right. So what we can start with, and it's often a good thing to start with in any normal distribution question, is a picture of the bell curve. And remember, it only has to be a rough little sort of thumbnail sketch. And we don't know the mean, so the mean might sit here. I'm just not going to mark it with mu there, but we don't know that number at this stage. The question said that 8% of the metal cuts are shorter than 12 millimeters. So if this was 12 millimeters along the x-axis here, and I sort of like to mark a line straight up just so you can visualize it a bit better. So we've got 8% of the distribution below that number. So that is 8% kind of in here, I suppose. I wanted to color it. And we've got 5% of metal cuts being longer than 19 millimeters. So 19 millimeters might be sort of somewhere up here. And we've got 5% of our distribution above 19 millimeters. Now, that obviously doesn't give me enough information to know what the mean and standard deviation are yet, but it gives us a bit of information to start with, and it also tells us that the mean has to clearly be somewhere between 12 millimeters and 19 millimeters. We're going to have to go a bit further to get the precise value of the mean and the standard deviation though. Okay, so for this particular distribution, the way that I've drawn it, the x-axis, the numbers along the x-axis would be representing the length of the metal screws, which often we might think of as being like, that might be the thing that we let x equal. If, though, we were to try to standardize these values and think of it more as a normal distribution, a standard normal distribution, I should say, where we know that the mean would be 0. All right, so I'm going to now think of this as being a standard normal distribution. Well, what we can do is we can use our calculator to come up with the equivalent z values for this 12 millimeters and 19 millimeters. So what I'm going to do here is I'm going to mark in the same spots and with the same percentages, so it's still going to be 5% above this number, 8% below this number here, but we're going to try to come up with these as z-scores. And the way we're going to do that is, so I guess I'm going to put a note here just saying, to get z values, we're going to use our CAS, we're going to use inverse norm CDF. Now this wouldn't really, I'm writing a different color here because on a saccharine exam, this really doesn't help me for working out. Calculated text is not acceptable working out, but just as an example, so we know where we're getting these values from, I'm going to show you how you can do this on the calculator. So we can just try to focus that a little bit better. So we're going to go interactive, distribution, inverse, and it's inverse norm CDF that we're going to use here. Now, for the 12 millimeter length, we knew that there was 8% of the distribution below 12 millimeters. So if I put this tail setting as to the left and put a probability of 0.08, because that's the percentage of the distribution that's below this number. But if I keep the standard deviation as 1 and the mean as 0, what I'm actually going to get is the standardized value for 12 millimeters, which is negative 1.40507. Okay, so I guess the equivalent Z value for our X value of 12 millimeters is negative 1.405, and I'm just going to say dot to dot because I'm really going to keep the full number in my calculator. Then, for the X value of 19 millimeters, I know I've got 5% of the distribution above 19 millimeters. So if I do the same thing here using inverse norm, but this time I say my tail setting's to the right because it's 5% above this particular number. Put in the probability as 0.05 because that's 5%. Again, leaving the standard deviation as 1 and the mean as 0, and hit OK. I get my standard score, my Z value for 19 millimeters, and that is 1.64 and so on. And again, I'm going to keep the full number in my calculator. So it's 1.64, dot, 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 dot. Now, what this tells me is that the standard score for x equals 12 millimeters is z equals negative 1.4 and so on. And then the standard score for x equals 19 millimeters is z equals 1.64 and then so on. And the reason this is helpful is because we have this formula that says whenever we want to calculate a standard score, we use z equals x minus the mean divided by the standard deviation. In other words, the standard score equals the actual score minus the mean divided by the standard deviation. That's a formula that works for normal distributions. In this question, we're trying to find the mean and the standard deviation. So it makes sense that we would want to use a formula that has the mean and the standard deviation in it. Now, what we can do is substitute some values into this formula because we know, for example, that when, well, let me write it. We know that when x equals 12, that z is equal to negative 1.405 dot, 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 dot. So if I substitute those two values into this formula, I get negative 1.405 equals 12 minus the mean, because I don't know that yet, divided by the standard deviation. So there's one equation with two unknowns. Now, if we're trying to solve for two unknowns, we're going to need another equation. That's fine, because we also have when x equals 19, z equals 1.64. Okay, and that gives me 1.64 is equal to 19 minus the mean divided by the standard deviation. And those two equations, we can call this one 1 and this one 2, they can be solved simultaneously for the mean and the standard deviation. So our next step is to put those two equations into our calculator using the simultaneous equations template. Now, remembering that I'm keeping the full numbers in my calculator here to make this as accurate as possible because you shouldn't round off until the end. So to bring up your simultaneous equation template, keyboard, math 1, and then this button here. And so it's, the first one was negative 1.4, oops, that hasn't copied where I wanted it to, is equal to, oops, I've just turned my calculator off. I was trying to be creative and use shift divide to get the fraction template. So it's 12 minus, now, rather than trying to find symbols for mu and sigma, I'm just going to use x and y. So it's x and y. And then the second equation was 1.644, and the rest equals 19 minus x over y. And I want my calculator to solve this for x and y, which are really the mean and standard deviation respectively. And there we go, we get our mean and standard deviation. And so the mean is equal to 15.22. Again, I keep letting you down with these questions. I keep forgetting to write what to round to, so let's just go 2 decimal places. And the standard deviation is 2.295, so that would be 2.30. And both of these would actually have units of millimeters. Okay, so in this particular question, the average length of these metal screws is 15.22 millimeters with a standard deviation of 2.30 millimeters. So a pretty complicated question there, but you can see what we've done is we've used this formula, this standard score formula, to find the mean and the standard deviation. And what we had to do was get a bit creative with norm CDF and use inverse norm CDF to calculate the Z scores for those X values that we had at the beginning. Okay, tricky question, but hopefully you can see how this formula can be used to solve for the mean or the standard deviation, or in this case, both. And we could solve for both because we were able to generate two equations. Okay. In another question that maybe is a bit more friendly, you might have only had to solve for one of them, which means you would only need to have generated one equation. Okay. Another sort of tricky context to these normal distribution questions can be when you have to use, I guess, comparing, and it's similar to what we just did, but comparing the distribution of a normally distributed variable back to the standard normal distribution. And sometimes you'll have to do this in questions without any real context, and this is where, as always, your bell curve sketches can really come in handy. Right, so in this question, we're being told to let x be a normally distributed variable with a mean of 10 and a standard deviation of 2. And z is just the standard normal distribution. Now you can see in part A, B, and C of this question, we're being asked to find all these values when we're really comparing the probabilities of z and probabilities with x. So we've got x's and z's and that sort of thing going on. In this kind of question, it's often best to sketch really what you might think of as like two distributions in one. And what I'm going to do is just get some sort of scrap paper here and sketch it so I can make it nice and clear for you. If we do, and try to do really quite a big bell curve here, make sure I've got that on the actual screen. So if here is the mean, and we usually sort of mark in 3 standard deviations above and 3 below, and I'll try to make them evenly spaced. That's a reasonable effort. Okay, so in terms of x, we had the mean of 10 and a standard deviation of 2. So 10, 12, 14, 16. So each of these markings being 1 standard deviation means they're all 2 units apart. But what I could also do on the same sketch is actually try to think of, and even write them underneath, the equivalent z-scores. Now remember that with the standard normal distribution, the mean is 0 and the standard deviation is just 1. And what this is going to let me do for this particular question is compare the values of x with their standardized values. Because, for example, an x value of 16 is equivalent to a standardized value of 3 in this question. And an x value of 8 is equivalent to a standardized value of -1 in this question. And so if I go back to what the question is asking me to do, it firstly says, state the value of a if the probability that z is greater than a is equal to the probability that x is greater than 14. So let's go back to this picture. So the probability that x is greater than 14, I could mark on my, let me use a different color here. Could mark this on the bell curve and say, well, really what this is asking about is being above 14. And the question says, state the value of a if the probability that z is greater than a is equal to the probability that x is greater than 14. So if I'm thinking about greater than 14 and greater than some value of z, well, it's quite clear for me to tell that the equivalent value of z is z equals 2. And so I can say that the probability that x is greater than 14 is equal to the probability that z is greater than 2, and therefore a is equal to 2. Right, really what that question was asking me to do, even though the notation looks complicated, is just compare the x value of 14 to find the equivalent z value. And clearly from this scale, the equivalent z value is 2. Okay, part B of the question says, state the value of b if the probability that x is less than b is equal to the probability that x is greater than 12. So notice that neither of these are referring to z, they're both referring to x. But we've got a switched around inequality. So I've got x less than b equal to probability x greater than 12. So again, I'm going to go back to this picture and find, I keep trying to use different colors here. So here's x equals 12. And one of my probabilities was the probability that x is greater than 12. So that would be from 12 and above. And then it was asking me to find what's the equivalent probability for x being less than a particular number. Now remember that these bell curves, these normal distributions, are symmetric. So the probability that x is greater than 12 is exactly the same as the probability that x is less than 8, right? If you allow for my freehand sketch not being perfect here, this center between 8 and 12 is symmetric, and so anything less than 8 and greater than 12, well, the percentages of the distribution we have in either of these sections are actually the same. And so the probability that x is greater than 12 would be the same as the probability that x is less than 8. So I can say probability that x is less than 8 equals probability that x is greater than 12, and therefore b is equal to 8. And finally, and this looks like a pretty tricky one, state the value of c if the probability that x is between 10 and 16 is the same as the probability that z is between c and 0. All right, so what I'm going to do is I'm going to take the one that's got just numbers in it, so the probability that x is between 10 and 16. I'm nearly out of colors here, but I've got one more up my sleeve. So the probability that x is between 10 and 16, and I'm going to extend that up. So the probability that x is between those two numbers needs to be the same as the probability that x is between, I beg your pardon, that z is between some other number and 0. So again, I'm going to have to use the symmetry of this bell curve and say, okay, well, from here to here, if I want an equivalent probability, I'm going to have to go from here to here. So those two sort of sections that I've marked with those blue arrows there, they should be equal to each other. Now, the first probability was framed as being between x equals 10 and x equals 16. But the other probability statement was written in terms of z. So that would have to be that z is between -3 and 0. And so what I can say is that the probability that z is between -3 and 0 is the same as the probability that x is between 10 and 16. So I've actually had to use some symmetry here from the two different sections. But again, if I fill in that statement, we're saying probably that x is between 10 and 16 is the equivalent to saying the probability that z is between -3 and 0. Well, then I can say, therefore, this c value is equal to -3. Right, so there's a bit to understand in those questions. One, because we have to read the notation carefully to even understand what the question is asking us. But two, because we're constantly having to make these comparisons between the standard normal distribution and the distribution of x that was given to us in the question. Some complicated stuff in this video. So as always, get in touch with your teachers if you need some extra explanation of example 2 or example 3. But otherwise, it's bye for now, and I'll see you in the next video.